Alrighty, howdy folks. Uh, let's look at 7.3, Trigonometric Substitution. And you see that I said courtesy Mr. Tommy Elliott. Yes, my colleague Tommy Elliott is a wonderful man, and he taught me he was doing these problems in a certain way, and I said, huh, that's really fascinating. And so I adopted his method, and of course he learned it from somebody else, but I thought it is appropriate that I credit Mr. Tommy Elliott. Cool. Here is the idea. Whenever you see an integral with a square minus x square, what is a? A is some constant, and x is of course the variable. For example, you may see 4 minus x square, right? Some square root of 4 minus x square typically. And in that case, a is 2, and or if you have square root of 9 minus x square, a is 3. If you have 5 minus x square, a is square root of 5. So it doesn't have to be that a doesn't have to be, rather a square doesn't have to be a perfect square. Okay? Okay. If you see this, then this is what you do. You construct a right triangle, and one of your sides is going to be a second side is going to be x, and the third side is going to be square root of a square minus x square. Does that make sense? One side is a, second side is x, and the third side is square root of a square minus x square. Well, in a right triangle like this, can I just arbitrarily assign, oh, okay, that the hypotenuse is square root of a square minus x square, the bottom side is a, and this one is x. Can I say that? No, I cannot. Because notice, the hypotenuse has to be the largest side, right? So here, could x actually be bigger than a? No, if x is bigger than a square minus x square would be a negative quantity, and so one of the sides is square root of that a negative quantity. So that's not possible. So clearly a must be greater than x, right? Also, when you subtract from a square and x square, what you get is a smaller number than a square. Let me repeat that. If you subtract x square from a square, what you get must be less than a square. So that square root must be less than a. You know all what I'm trying to say? That all I'm saying is a's got to be the biggest side based on this. Cool? So biggest side means hypotenuse. Hypotenuse has to be a. I apologize. I think I made it a much bigger deal than I needed to. Okay, so the hypotenuse is a, and one of the sides is x, and the third side is a square root of a square minus x square. Pythagoras theorem. So, which one should we pick as x? It really doesn't matter. But I don't know. For some reason, I make the vertical one x if I can. I make the vertical one as x. Okay? And so, by Pythagoras theorem, the bottom one is square root of a square minus x square. Cool? All right. And then, you can label any one of these non-90 degree angles, non-right angles as theta. So I happen to pick this as theta. Cool. After you do this, you make a ratio. You make two ratios. One is x over a, and the second one is square root of a square minus x square over a. Notice something. In all these ratios, the denominator is always that constant. You want that. Okay, so first ratio is x over a. Well, by trigonometry, what is that ratio x over a when in terms of theta? You remember that SOHCAHTOA mnemonic? sine opposite over hypotenuse, cosine adjacent over hypotenuse, tangent is opposite over adjacent. That SOHCAHTOA tells you that sine theta must be x over a, or x over a must be sine theta. And that tells you x must be a sine theta. Right? And another ratio, like I said, is you form square root of a square minus x square over a. What is that in terms of this theta? Well, that is nothing but adjacent over hypotenuse, which is cosine. So square root of a square minus x square over a is cosine theta, which means square root of a square minus x square must be a cosine theta. Cool? So this is kind of stuff that we do. I know I went through a lot of steps, but please follow them. Why? What are you trying to do here, man? Here is the idea. This is called trigonometric substitution, right? Where, notice eventually what we got by drawing the triangle and doing all this nonsense. We got x, the variable x, to be a constant a times sine theta. Variable x in terms of constant and theta. And also we have x involved here, square root of a square minus x square. Even that has been expressed as a constant and theta. That is what we are trying to achieve. These are the things that we are going to substitute. Wherever we see x, we will substitute a sine theta. Wherever we see square root of a square minus x square, we'll substitute a cosine theta. I will solve tons of problems so that this concept is crystal clear, okay? So if you've got it, rewind it, that's good. If you didn't get it, rewind it and watch once more. And in fact, I'll make it more clear by giving 2 more cases like this. Cool. A square minus x square, we are done with that. Now, what if we were to have a square plus x square, right? Well, again, we draw a right triangle. And again, we'll have one side is a, the second side would be x, and the third side would be square root of a square plus x square. Now, logically, which one has to be that square root of a square plus x square? Right? Is square root of a square plus x square bigger than a? Yes. Is that bigger than x? Yes. So square root of a square plus x square is the biggest side, and that has to be the hypotenuse, clearly. Right? And now one of the sides is a and the other side is x. Like I said, just go ahead and make the vertical always x if you can. And so we have x, a, and square root of a square plus x square. And again, theta could be either this acute angle or that acute angle, doesn't matter. And if you pick this as theta, then we have to do what next? Make ratios. What ratios? 2 ratios. X over the constant. First ratio. Second ratio, square root of a square plus x square, that stuff, over a. Right? Let's do that. Now tell me, so far as this theta is concerned, this side is called what in terms of opposite adjacent hypotenuse? Would you agree? X is the opposite of theta. Similarly, is a the adjacent of theta? Yep, so we have opposite over adjacent for x over a. What is opposite over adjacent? Which trig ratio? Tangent theta. So we will say x over a equals tangent theta, which implies x equals a tangent theta. I just multiplied both sides by a. Okay. Again, let's form this other ratio. Square root of a square plus x square over a, in this case, would be hypotenuse over adjacent, which is the reciprocal of cosine, which is secant. And so square root of a square plus a square over a is secant theta, which implies square root of a square plus x square is a secant theta. Simple enough? That's the idea. And one last case. Can you guess what that case must be? A square minus x square, we are done with that. A square plus x square. Should we do x square plus a square? Nah, a square plus x square plus a square, they are both the same. What do you think? If you said x square minus a square, you are absolutely right. Yes, x square minus a square, if an integral contains that. Again, draw a right triangle. Decide which one. There are three sides, x, a, and square root of x square minus a square. What's the biggest side? We got x square minus a square, right? So x has to be the biggest side. So the hypotenuse is x, and one side is a. Let's make the bottom as a, and square root of a x square minus a square is the vertical side. Again, theta, ratio, x over a. X over a, what do you think x over a is? For theta, x is the hypotenuse, a is the adjacent. Hypotenuse over adjacent, reciprocal of cosine, that is secant. So x over a is secant theta, x equals a secant theta. Again, square root of x square minus a square over a, opposite over adjacent is tangent, and so we get square root of x square minus a square equals a tangent theta. Cool? This is the idea. Now, I'm going to demonstrate all of this, how this is going to be useful in solving certain integrals. I don't need this. Oh, brother. Okay, let's get to this one. Uh-oh. How do we figure this integral out? Do we have something of that form, a square minus x square minus a square plus x square here? Yep, we do, right? And because we see a square minus x square, let's go ahead and do trig substitution, for which let's draw our triangle. Cool. What is a here? Be careful. Don't say a is 4. A is 2. Right? So which one is the biggest side? 2x and square root of 4 minus x square. There are three sides, 2x and square root of 4 minus x square. 2 must be the biggest one. Right? So that's got to be the hypotenuse. And like I said, if possible, make the vertical as x, and so the other one has to be square root of 4 minus x square. And label it theta. Right? What next? Ratio. Yep. X over 2 must be opposite over hypotenuse, which is sine theta. So x over 2 is sine theta. X equals 2 sine theta. And right after you do this, do one more thing. Figure out what dx would be. If x is 2 sine theta, what is dx, the differential? You take the derivative of the right hand side and multiply by d theta. 2 sine theta, the derivative is 2 cosine theta, with respect to theta of course, is the prime of it, is 2 cosine theta. So dx is equal to 2 cosine theta d theta. Cool? Next, we'll form the other ratio, square root of 4 minus x square over 2. And that's going to be adjacent over hypotenuse, which is cosine of theta. And based on that, let's figure out square root of 4 minus x squared by multiplying both sides by 2. Cool? Now, notice, why did we go through all this stuff? We have x in terms of 2 and theta, dx in terms of constants and theta, square root of 4 minus x squared in terms of constant and theta. So that's the idea. We are ready to make our substitutions. That's exactly what I'm going to do. I'm going to replace square root of 4 minus x squared with a 2 cosine theta, dx with a 2 cosine theta d theta over x square. x is 2 sine theta, so x square must be 4 sine square theta. Cool? So here we have all the substitutions done in terms of trig functions. There is no x showing up or a dx showing up at this stage, right? That's what you want. Okay, let's try to simplify this. 2 times 2 is 4, and this 4 over 4 is 1. Cosine theta times cosine theta is cosine square theta. Cosine square theta over sine square theta is cotangent square theta. Right? Can we solve this integral? Can we figure this integral out? Yeah. Remember, how did we... how should I put it? Okay. When I see this one, to me it looks like integral tangent square x dx. Oh, that one we say secant square x minus 1 and then integrate. Same or similar thing here. Cotangent square theta is cosecant square theta minus 1. If you recall that identity, then we are almost in business. The integral of cosecant square theta is negative cotangent theta, and integral of 1 is theta. That's what I wrote. Cool? Plus c. Are we done? Not quite. Because this answer that we got right now is in terms of theta. The original problem is in terms of x. So it's our business to figure out what all of this would be in terms of x. Don't leave the answer in terms of theta. Okay? Okay, is that easy? Yeah. Cotangent theta. Looking at the triangle, can you tell me what cotangent theta has to be? First of all, in terms of opposite, hypotenuse, adjacent, and opposite, what is cotangent theta? It's the reciprocal of tangent, right? Tangent is opposite over adjacent. So cotangent must be adjacent over opposite. Does that make sense? Tangent is opposite over adjacent, TOA, T-O-A. So cotangent must be adjacent over opposite. Adjacent is square root of 4 minus x square. Opposite is x. So piece of cake. Cotangent theta is square root of 4 minus x square over x. There's a negative. We'll put that. But then, wait. What in the world is theta in terms of x? Right? So that's a slightly interesting question. Well, we have x equals 2 sine theta, which means sine theta must be x over 2. I could have looked at that one. Sine theta is x over 2. If sine theta is x over 2, can you tell me what theta itself must be? See my question? If sine theta is x over 2, what should theta be? Yep, theta must be sine inverse of x over 2, or arc sine of x over 2. That's the idea. And that's exactly what I substituted here. Cool? Look at this problem once again, rewind, and try to understand it and see how the steps are logically flowing. Once you understand the logic of it, you will notice that for the remaining problems, I'll do pretty much the same thing. Same logic I apply. Now, what if we have square root of x square minus 4 over x square? What does this look like? Hey, you have an x square minus a square, man. Yep, you're right. In that case, let's go and draw our right triangle. Which one is the biggest side? There are 3 sides. One of them has to be x, the second side has to be 2, and the third side is square root of x square minus 4. The biggest side has to be x, right? So that means the hypotenuse is x, and the constant, make that the horizontal one, 2. And so that means the opposite would be square root of x square. The vertical would be square root of x square minus 4. Let's call this as theta. Okay. Now, maybe it's about time I point out. Hey, what's going to happen if I put this other angle as my theta, man? Well, in that case, how should I put it? Give me half a second. Let me come back to it in just a second. Okay, with this, now what is that next thing? X over 2. We need to form the ratio, right? X over the constant. X over 2 is secant theta. So x equals 2 secant theta. Now maybe I'll try to answer that question. What would have happened if we had this other acute angle as theta? Then what would this ratio x over 2 have become? Then that would have been hypotenuse over opposite. Would you agree? If we had called this other angle as theta, then we would have had x over 2 being hypotenuse over opposite and not hypotenuse over adjacent like we have now. What is that? That's going to be cosecant theta. Well, x would be 2 cosecant theta in that case. Nothing wrong with that. You can still work the problem out. Okay, that's the only difference. Now, cool. Let's continue. What's the next thing? The other, oh no, dx. We need to figure out dx. Dx is 2 secant theta tangent theta d theta, because the derivative of secant theta is secant theta tangent theta, right? Now let's form the other ratios. Square root of x minus 4 over 2. And that's opposite over adjacent, which is tangent theta. And that's what I wrote. And let's multiply both sides by 2. Are we ready to make our substitutions? You bet. So we say for square root of x square minus 4, we plug in 2 tangent theta. For dx, we plug in 2 secant theta tangent theta d theta. For x square, we plug in 2 secant theta, the quantity square, which is 4 secant square theta. And the rest is just multiply and simplify. And trust me, that turns out to be, or you can do it, don't trust me. You verify yourself. Tangent square theta over secant theta. Okay. How do you evaluate this integral? Do you agree that now at this stage, this problem has become a problem like in 7.2? All trig functions, integrals of trig functions. That's the idea. So if you must master 7.2 in order to be able to do well in this particular section. Okay, any thoughts? Maybe you could pause and say, challenge yourself. Let me see how I'm going to integrate this. And you go ahead and integrate. Okay, here is my thought. Secant square theta minus 1 over secant theta. All right, and then I split that into secant square theta over secant theta minus 1 over secant theta and solved it like that. We know secant theta, integral of secant theta is natural log of absolute value of secant theta plus tangent theta, and the integral of cosine theta is sine theta, and so we end up getting this. Cool. Could you have done it by some other method? Yeah. In fact, you could have said this is, you could have written tangent square theta as sine square theta over cosine square theta. And secant theta as 1 over cosine theta. So let me see. That would have reduced to sine square theta cosine theta. Am I right? Sine square theta over cosine theta, 1 over cosine theta. Sine square theta over cosine theta. Ooh, that would have become sine square theta over cosine theta. And from that you could have figured out. Okay. Yeah, that's right. So there's more than one ways to solve the problem. What's that American expression? There are more than one ways to skin the cat. I don't know who came up with that? Why do they want to skin cats? I don't know. Whenever I hear that, all I have to say is, I want to add, there are more than one ways to skin the cat, none of which the cat likes. Cool, let's move on. So natural log of absolute value of secant theta. So now, do we know what secant theta is in terms of x? Yep, it's already given here. Or we could look at the triangle and replace secant theta with x over 2 and tangent theta with a square root of x squared minus 4 over 2, and we're done. And sine theta, sine theta, there is a sine theta. Sine theta is opposite over hypotenuse, and that's what I did. Cool. Are you beginning to get a hang of this one? Wonderful. Well, I did a problem with a square minus x squared. The second one was x squared minus a squared, and obviously this is x squared plus a squared. Just wanted to demonstrate all three of those. Okay, triangle. Biggest side is square root of x squared plus 4. So the vertical is x, the horizontal is the constant 2, and the hypotenuse is square root of x squared plus 4. As before, theta. Ratio x over 2 is tangent theta. X equals 2 tangent theta. What next? dx. dx is 2 secant square theta d theta. And the other ratio, square root of x squared plus 4 over the constant 2. That's nothing but secant theta. Multiply both sides by 2. Right? Are we ready for substitutions? You bet. So x cube. X is 2 tangent theta. So x cube is going to be 8 tangent cube theta. Right? 2 cube is 8 tangent cube theta. On the top, dx is 2 secant square theta d theta. Square root of x squared plus 4 is 2 secant theta. Those are the quantities I would have plugged in. Yep. And if you simplify, this is going to be 8 tangent cube theta secant theta d theta. The question is, how do we integrate this? If you recall, integral tangent to the mx secant to the nx dx, if the power of tangent is odd, right? Save a factor of secant theta tangent theta. That's what we did. That's exactly what I applied. And we're going to plug in u equals secant theta. And for that, let's rewrite this tangent square theta, secant square theta minus 1. And let's plug in w equals secant theta, dw secant theta tangent theta d theta. This stuff you should know, right? And that's it. 8 secant cube theta over 3 minus secant theta. We know what secant theta is, and so let's plug all that stuff in, and this reduces to this. Okay, so what happened, man? Yeah, there is a square root of x squared plus 4 over 2, the quantity cube and all that. Trust me on this one. You verify what I got is right. I think it is right. Okay. There we go. One more problem. To do this problem, I need to talk about completing the square. Raise your hand if you hated this stupid thing called completing the square. I know, every semester I have a whole bunch of that. Oh, I hate that. I got good news. I'll show you a way where it becomes piece of cake. There is nothing to this stupid completing the square. It's a very simple thing. I don't know why people make it so complicated. Check this out. If you have x squared plus bx plus c, okay, all you need to do is add b over 2 the quantity square. Can you remember that? If you have x square plus bx plus c, add b over 2 the quantity square. But notice, I said this is equal to. But what happened to your c, man? And how can you just add b over 2 the quantity square? Anything you like, you please. Yeah. Don't worry. Because we added b over 2 the quantity square, let's compensate for it by subtracting b over 2 the quantity square. There's nothing wrong with that, right? You can add something to an expression as long as you subtract that same thing from that expression. Okay, so that's gone, and there was a plus c, and dutifully we wrote back that plus c. Okay, why did you do this, man? It's because the first three terms now form a perfect square. Which perfect square? X plus b halves the quantity square. X plus the quantity b over 2, the whole thing squared. That's the whole idea. All right. Let me illustrate this with examples. So we'll replace all of that with x plus b over 2 the quantity square, and there's a minus b square over 4 plus c. This is the whole idea. Now, I have this also. All right, what if you had x square minus bx plus c? Guess what? You do the same thing. You just add negative b over 2 the quantity square. Okay, you add negative b over 2 the quantity square and immediately subtract that same quantity and you have a plus c. When you do that, the first three terms form the perfect square x minus b over 2 the quantity square. Cool? Now let's look at some concrete examples. X squared plus 4x plus 13. Well, does that look like x squared plus bx plus c? Yup. What is b? 4. What should we do? Add b over 2 the quantity square and subtract that same quantity. B over 2 is 4 over 2, right? Which is 2. So we add 2 square and subtract 2 square. I was even being patient. So added 4 over 2 the quantity square, subtract 4 over 2 the quantity square, and there's a plus 13. Be sure to write that plus 13. Now what happens? The first three terms form x plus b over 2. And now we can reduce it to 2 and say that's just x plus 2 the quantity square minus 2 square is 4 minus 4 plus 13. But minus 4 plus 13 is plus 9. So this whole thing reduces to x plus 2 the quantity square plus 9. Ta-da! This is what is completing the square. Simple? Let's look at, I think, one more problem. X squared minus 8x plus 20. Does it look like x squared minus bx plus c? Yep, it does. B is equal to 8 with a minus if you want, or you can look at it as, hey, b is negative 8. So we add negative 8 over 2 the quantity square and subtract that same quantity, negative 8 over 2 the quantity square. The first three terms now form the perfect square x minus b over 2 the quantity square, that is x minus 4 the quantity square, and we have a negative 8 over 2 is negative 4, negative 4 the quantity square is 16, so minus 16 plus 20, and that reduces to this. Cool? All right. I have another one. What if we have something like this? notice this is not quite in the form of x squared plus bx plus c, right? X squared plus bx plus c has a coefficient of x squared is just 1, but the leading coefficient is 1. But now we have a leading coefficient to be 3. What do we do in a case like this? This is the idea. Always factor out the leading coefficient. So 3 times the quantity x squared plus 4x plus 13. Now, for the stuff, now we are back to this original problem, x squared plus 4x plus 13. So complete the square on that inside the parenthesis stuff by doing adding the b over 2, the quantity square and all that stuff. That's it. Right? So no sweat. As long as you factor out the coefficient of x squared out, then you can apply the concept to that also. All right. So why do we need all of this? What has this got to do with integration, especially trig substitution? That's because we want to look at a problem like this. We notice that we have a square root of x squared plus 4x plus 13. That doesn't look anything like what we have done in trig substitution. That's not like x squared plus a squared or x squared minus a squared or a squared minus x squared. What in the world is this doing here? Well, the thing is, if we do a completing the square on x squared plus 4x plus 13, we've already done that in the previous slide, right? So I'm going to invoke that result. Notice we can write that as the quantity 1 over square root of the quantity x plus 2 square plus 3 square. Right? Perhaps I could have done this, but I didn't do it. Guess what? You can think of this as just x plus 2 as a y, and dx would be dy, which means this becomes dy over square root of y square plus 3 square. I didn't do that. I just looked at it as, what the heck. I'm going to draw a triangle, and I'm going to make one of the sides x plus 2 and the vertical side to be x plus 2 and this as 3. And so that means the hypotenuse must be this, and proceeded as if, this x plus 2 was just like a simple x. And that works. So again, we'll form that ratio dx, x plus 2 over 3 equals tangent theta, and x plus 2 equals 3 tangent theta. Dx, differentiate both sides, and you get dx on the left hand side and 3 secant square theta d theta on the right hand side. Right? It didn't make any difference. We definitely need dx, right, for the integral. And yeah, even if you have x plus 2 as opposed to a simple x, we can still carry out the differentiation. And so dx is 3 secant square theta d theta. And the other ratio, the big long thing, square root of blah blah over the constant, and that is equal to hypotenuse over adjacent, which is secant theta. That's what I wrote. And so that means multiply both sides by 3 and you get that to be this. Are we ready to make substitutions? Yep. And so dx is 3 secant square theta d theta, and square root of x squared plus that is 3 secant theta. And so this reduces to just simply integral secant theta, which we know is natural log of absolute value of secant theta plus tangent theta plus c. Plug back in terms of x. Do we know secant theta? Yep. We can read it either off of the triangle, or we can look at this expression here. That tells you. And tangent theta also we know. Just plug those things in. You're done.